capacitor and a coaxial capacitor. I have no idea, like, no script, so let's just go for it. Boom, boom, boom. Parallel plates. Well, you could use Gauss's law. Let's just do it then. Boom, boom, boom. We can call that A, plus, 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 plus. This has some sort of density, right? It'd be area density, so it'd be dq dA, right? So I don't know, dq equals the sigma dA. Or if it was uniform, right? We don't have to do it that way. If it's uniform, we can play this game. Q over A, right? And we can think of that A as that A, and this Q is Q enclosed by that cylinder. Okay, great. Gauss's law. What is Gauss's law? I have no clue. Oh yeah, E dot dA equals Q enclosed over A. All these derivations have a whole right side you got to work on, a whole left side. Let's work on the right side. You could multiply. You could say that Q enclosed right here is sigma A. So I can do that. I could change this to sigma A. This is epsilon naught, of course. Epsilon naught. All right, I think I'm done with this side. Why did we use Gauss's law? So we use Gauss's law when we have electric fields that behave on a regular sort of systematic basis, and we can define this surface. So, all right, so it's interacting here. There's flux there. There's none. So I can pop E out. But there's flux down here too. All right, so my A is really top and bottom where there's flux, so it's 2 times A. If A is just the area of one of these circles at the top and bottom of that. So boom, A, epsilon naught. So the electric field around, it's not a parallel plate capacitor yet, it's just a 2-dimensional sheet, is this over, I'm just going to write it out, A, 2A, epsilon naught. So here's the answer. Boom. So everywhere in the whole universe, if you had an infinitely big sheet of charge, you would change the electric field by that, and it has no function of R. It just changes it everywhere in the universe. But you can't have an infinitely large sheet, so you can't have that, but you could approximate that when you get next to it. Okay, you throw another sheet in there, bam, 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 bam. Parallel plate capacitors, the charge comes from here, goes to there if you're talking about electrons by hooking up a battery. And now what happens is you're going to have an electric field that goes, let's see, plus goes this way. It's going to go this way. At double the strength. So inside you're going to have one going this way, one going this way. So here you go. Parallel plate capacitors, E equals this over epsilon naught. And outside they disagree, right? Outside is going this way, but the top plate is going to be causing it to go that way. We know it's not a function of R, so these are the same right there, and they cancel. Oops, I made it the same. It goes like this, down, 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 versus up, 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 and they cancel. So there you go. That's the strength of your electric field in a parallel plate capacitor. Whenever you do these capacitor derivations, step 1, you use Gauss's law to find E. Then 2, use this definition. I'm going to ignore the minus sign. Well, I'll leave it in there for now. But okay, use the E you found, plug it in there, and then the last step is super simple, right? It's capacitance is what? It's the amount of charge you can store per here. So you take, you take this there, you take this there, and took that from here. Okay, we did that. So let's just do step 2. Like E equals epsilon naught over that. We used Gauss's law and did that. Now delta V equals the integral of E. Well, this epsilon naught. Okay, I don't know. Say this is D, the distance of D away. And so you could say, R equals 0 to R equals D, dr. forget the minus sign. Delta V, so it's just this over this times D. And this is a fundamental equation you want to remember for parallel plate capacitors. Those are the most common. So that's kind of interesting. That can tell you stuff. If you change D and leave that the same, you're gonna double this, double that kind of thing. If you have the same charge density. Okay, but then last step, let's do it. Number 3, C equals Q. Well, what is Q? Q is lambda A, right? And delta V is that, so I'll put epsilon naught into that. This doesn't seem like it should. But I guess it's gonna. Don't fail me now. Q is that, and then I'm just putting that there and D there. This cancels, I guess, and you have A epsilon naught over D, right? That's the fundamental equation for a parallel plate capacitor in air or in a vacuum. What we see in reality is that we throw a K in here, right? Where this is the dielectric constant, so you can make it go up by putting a piece of plastic in there, and we can talk about why that happens, but you do put a piece of plastic in between a parallel plate capacitor, you start to you polarize all the little the atoms, you should look it up, and that creates electric field that weakens the one that exists, but the one that exists is still going to be given by that function over there, and you're going to be able to store more charge. So there you go, fundamental equation for parallel plate capacitor.